So the first one is a question about the drivers for us to choose the WACA vessel shape, and if we could qualify the dependence of these results to the vessel shape. So I will take the first part of the question, and maybe I can let you, Tanguy, Pierre-Alain, or Melissa address the second part of the questions. So, so we decided in FLOWTOM project to study one specific MCR solution, so the self-erecting solution. And so we collaborate with an external partner, and they provide the specification of their solution, and also what could be a vessel to handle this solution. So it was a package of vessel plus solution. So we're not today displaying the name of either the company or the solution. So that is the driver of why choosing the WACA vessel shape and how it impacted the results. Maybe Tanguy, Pierre-Alain, or Melissa, you can...
Yes, I can try to answer. So yeah, at first the vessel is about 185 meters long because we rescaled the original tanker that was provided to us. So this is to have another rough idea of the shape of the vessel, and the dependence on the result with the vessel. So it's mostly impacted by the motion in roll of the vessel, which the period is around 10.5 seconds, as I said in the presentations. What we observed during the simulations is that the most impacting thing in the operability is the pendulum motion, and it arrived first and after the Windsor-Knudsen roll motion. So I don't know if I can quantify it, but I would say it's very dependent on the pendulum motion, especially so in the length of the crane line, because it's directly linked with the pendulum period. So the pendulum is entering directly in excitation with the systate peak period. So this is why, for example, in the case 3, we have a lot of failure at 7 seconds, and in the Mediterranean Sea, when we can have more failure in the AO5 site with the long pendulum length with the first case with the big package. And the oscillation of the Windsor-Knudsen of the vessel is not very impacting the motion of the pendulum, in fact. So it's secondary. I don't know if that answered the question. I see there is a second question of the distance between the ship and the floater. It was at 15 meters, if I'm right. This distance was chosen to be the kind of listening to expert of operation. It was the kind of distance that a captain would allow to go as far to a floater, and we thought that lower than 15 meters it was difficult to manage the distance with the dynamic positioning and with the vessel. What is linked with the reach? Yeah, it was linked with the reach of the crane. We chose the crane to be able to perform the lift, because the first lift, so the package 1, is have an important height, so more than 35 meters. So we needed to have the crane capacity to lift at this height. So yeah, it was linked.
Okay, so there is another question about the temporary self-erecting crane being quite heavy with high COG. So did you investigate how the dynamics of the foundation are affected after addition of the crane vs previous? So maybe you can discuss about the case 4.
Yeah, you can if you want
maybe I can take it. So yeah, we have done 2 cases for this one to try investigate this. The first case was the case 4, which is a survival case with the weight of the system, which is lowered to the base, to the transition piece level of the floater. So lower impact in terms of COG, but impacts in terms of weight included in the foundation. And both floaters have succeeded in the criteria we defined for a survival case. And also we defined this case 2, which was the blade integration. So with the weight of the system at the top of the tower, including the weight of the blade, which is clamped on the system. And for this, we compared the motions of both floaters together, but we did not perform the detailed comparison of the floater with and without the system. However, I can talk about the TLP because I know it a bit. We did not observe significant changes in behavior once the system is integrated.
So there is another question about the limitations in the numerical studies. There is no particular reference for these limitations. In fact, there is a consortium of partners for the FLOWTOM project, in which there is some experts in marine operations. So this was more a discussion with one or another partners to define this criterion.
Oh, yes. So could some dampers or motion absorber added on the lifting device help on reaching a possible and accurate contact, for example, between bolted flanges to connect? If not, could your studies drive to quick coupling solution between parts with more tolerance than bolt and nuts? Maybe Pierre-Alain, if you want to address this?
I can try. Well, we have not investigated this level of detail, but yeah, this was quite the conclusion we had for the case 3, where we modeled just a lifted package with a pendulum. When I was in the conclusion explaining that this was not sufficient in terms of solutions and we will need more accurate Tugger lines modelization, including some stoppers or guidance systems. What is mentioned here is actually a part of the solution. Now, how to model it in a simulation, to be honest, I'm not able to answer this question now.
Just to add more on that, I don't know if we mentioned it today, but the post-treatment of the simulation was we produced a time series of 3-hour simulations, and we cut this time series in windows of 10 minutes. And then we look at the maximum value around this all of these 10-minute windows, and then we operate a mean value of all the maximum value around the 10-minute windows, and that's what is creating the result behind the figure we are showing today. And this is well adapted for the blade exchange or for the package float-to-float transfer, because this is the kind of time windows that can happen before a lift or before a contact with the dampers. However, for the case 3, where we are looking at the hub transfer, it's possible that the hub would be very constrained with a different solution with damper, with fenders, or with contact and maintained during the operation. And so the time windows of 10 minutes where the hub is oscillating is maybe not realistic here. Maybe it would be a narrower window.
Okay, maybe we can take another question. Yes. Question for Pierre-Alain. In case there is an MCR to perform on the PGL project in the near future, how would you use the result of FLOWTOM?
Well, actually, for PGL project, I think it will be more complicated because I mentioned the survival case before, and the increase of weight due to the system we used was working with our FLOWT for wind project, which is a floater developed for a 15 megawatt turbine, which is bigger than PGL project. And I think for PGL, it will not work, and the additional weight will be too big. So that's a conclusion we can have from FLOWTOM. Maybe not the one we would expect, but this is quite unlikely to see it for PGL. We'll need further studies, but will be complicated.
Okay, but as the FLOWTOM project also looked at developing a methodology and not only look into one MCR solution, I would say that FLOWTOM's methodology is now available to be used to assess other MCR solutions. So as a global conclusion, so now we have benchmarked the 3 simulation tools in between themselves and with basin tests. So we looked also at their sensibility toward more operating criteria. So looking now at real cases would help to be more precise on the methodology assessment. So I would say as a FLOWTOM project leader that you could use the methodology of FLOWTOM to assess MCR, any kind of MCR solution on PGL future projects.